Hey guys, it's Miss Simmons. I'm sorry I can't be there today, but you guys know that the show must go on, especially in an advanced or accelerated level class. So today your topic is prime factorization and greatest common factor. So what we're going to be doing is using prime factorization to find the greatest common factor of two numbers. So you'll see the topic and the essential question written on the screen in front of you. If you guys want a notes sheet, remember they're on the front table. Just ask Miss Fenimore for one. Okay, so how can I use prime factorization to find the greatest common factor of two numbers? Well, first of all, you have to know what factors are. So factors are two numbers that are multiplied together to make the original number. So essentially what you're doing is taking your original number and breaking it down into multiplication facts. So for example, 18 has the factors of 1 and 18. It also has the factors of 2 and 9. And it also has the factors of 3 and 6. And the reason why I know that I can't go any further with factors there is because nothing between 3 and 6 can be multiplied together to make 18. So as you can see, some numbers have multiple factors while others have less than what 18 has. So for 35, I could do 1 times 35. I could do not 2, not 3, not 4, but I could use 5 times 7. And remember, if we do the reverse of these, like 35 times 1 or 7 times 5, that's exactly the same. So we don't want to list those twice. So as you can see by comparison, 18 has more factors than 35, for instance. So if you look here, you can see the definition of factors, and then you've got two examples of what factors are. I'm going to replace these ands with multiplication symbols. Remember, we don't really want to use this x. We should probably be using the star because we are about to move into the algebra world where an x is a variable and not the multiplication symbol. So remember to have that in your notes as well. Okay, so moving forward. Prime factorization. So now that you know what a factor is, you can actually break down a number into just its prime factors to create your original number. So prime factorization is going to be when you are finding those prime numbers that you could multiply together to make the original number. So here's an example of a breakdown of 100. You could do 10 times 10. You guys know that there are more than just the multiplication fact of 10 times 10. You could do 2 times 50, you could do 4 times 25. There are a lot of different options here. But in this particular example, we chose 10 times 10. And then what you do from there, after you've broken it down, is you say, okay, well, 10 and 10 can both be broken down further into 2 and 5, and then 2 and 5 again. Right here, what you've done is taken your prime factors and you've written this is called expanded form. And what expanded form is when you take all the prime factors and you literally just list them written out. It is important that you write them from least to greatest. That is the standard way to write expanded form. Below that, you'll see what's called exponential form. And the only difference between this and expanded form is that you've taken the numbers that you were given and you've written them with an exponent. So this number 2 is the base number. It's what is repeated. And then this exponent, the small number here, that's how many times it's repeated. So you can do that again with your 5s. You've got a 5 here, which is the base number. That's what is being repeated. And then the exponent represents how many times it's repeated. All right, so what is a prime number? Because I just told you that you had to break the number down into its prime numbers. So a prime number is a number whose only factors are 1 in itself. Fun fact, the only even prime number is the number 2. And then I've given you this nice list of common prime numbers that you probably want to write down, guys. It's something that is just really helpful to have on hand. So the opposite of a prime number would be a composite number. And a composite number just means that it's a number that has more than 2 factors. So if you flash back to that second slide that we looked at, where we listed the factors of 18 and 35. Both 18 and 35 are composite numbers, which means that you could list more than one multiplication fact for them, more than just one times that number. A common misconception is that all composite numbers have to be even. That is not true. Take the number 51, for example. 51 can actually be broken down into 17 times 3, as well as you could do 1 times 51. But again, it's got more factors than just 1 times itself. The number 1, on the other hand, is neither prime nor composite, because if you look at the factors of 1, the only thing that makes 1 is 1 times 1. And since 1 is already itself, it cannot be a prime number because it's supposed to have 2 factors. A prime number has 2 factors, and that is 1 in itself. 1 only has the 1, which is 1. Okay, so remember, you guys can pause this at any time. If you feel like I'm going too fast, pause it and rewind, okay? So moving forward, you can find the prime factorization of a number by creating what's called a factor tree. Now, these are pre-laid out factor trees, so remember, there are more than one option for just breaking down this 80. I'm pointing at the screen. I know you guys can't see that, so I should probably use my cursor. But in this case, we're going to start with the number 2 times 40 to create 80. Okay, notice that 2 is in this little circle right here, and what that should tell you is that it is a prime number. You cannot break that number down into anything other than 2 times 1 at that point, because it is prime. You don't want any 1s in your factor tree. Do not put any 1s in your factor tree. There is one exception to that rule, and it's when you're dealing with a prime number already. So now I want to go and break down this 40 because it's still composite. So the next thing I'm going to use is 2 times 20, because I know that 4 times 10 is 40, but again, 4 is composite as well as 10. Those can both be broken down further. So I've got another 2 here that's prime. So I'm going to break down 20. That would be 2 and 10. And then 10 is my other composite number, which will break down into 2 and 5. Okay, so when I write this in expanded form, remember, I want to write this in numerical order, meaning from least to greatest. So when I write it, I know that I've got a 2 times a 2 times another 2. If you count it up, we've got 1, 2, 3, 4 2's here that we've got to list. So 1, 2, 2 2's, 3 2's, another 2, and then my last number here is a 5. So with expanded form, I've got 2 times 2 times 2 times 2 times 5. Okay, so to write that in exponential form, on the other hand, I take my base number, so what's being repeated, that would be the 2, and it's repeated 4 times, so that's my exponent. Then I've got one lone 5 at the end. The 5 does not need an exponent because it's only repeated 1 time. You could put an exponent of 1, but that's sort of a waste of time because since there's a 5 there, we know it's only there 1 time. Okay, so this is expanded. That means it's written all the way out. Everything is listed. With exponential form, you're shortening it. You're trying to make it more compact. Okay, so let's do another one. You've got 16. So again, you could break 16 down into a couple of different things, but these pre-made layouts kind of restrict your creativity with your multiplication facts. So the only thing I can think of that starts with a prime is 2 times 8, because if you look back at your list of common primes, 2 is probably one of your most common of those common. Then I know that 8 is composite, so I need to break it down further. That would be an 8 and a 4, or excuse me, a 2 and a 4. And then that 4 is the last thing I have to break down, which would be a 2 and a 2. Now remember, when you're listing expanded form, you do not want to list these composite numbers. You only want to list the prime numbers, only prime numbers. So that will be 2 times 2 times 2 times 2. And you can double check yourself to make sure that's right by actually going back and multiplying those numbers together to see if you get your top number in the tree. So 2 times 2 would be 4, 4 times 2 is 8, and then 8 times 2 would be 16. So I know that I have my answer correct. Now when I write that in exponential form, since I've only got one factor that's being repeated, remember you look at what is being repeated, which in this case is the 2, and then your exponent lists how many times it is repeated. So in this case it's 4. And now I have used all of my base numbers, so this is all you have to write for exponential form. In this case it's 2 to the 4th power. Okay, so I'm going to show you guys how you don't always have to start with a prime number, so just deal with me here. You can start with a 16, and remember there's more than one multiplication fact that makes 16 here. So you could break that down in theory into 4 and 4, because 4 times 4 is 16. Now when you do that, what you've done is you've broken it down into 2 more composite numbers. So you don't want to put a circle around those. You actually just want to keep breaking them down, because 4 and 4 can both be broken down into the prime numbers of 2 times 2. Now in this case, this is when you would want to circle, and forgive me because I'm working without a mouse here and not on my board. I'm going to try and circle these as best I can. They kind of look like terrible, terrible squares. Oh yeah, that's beautiful. Okay. So then you want to break down your other 4 here, which will still give you 2 times 2, because that's the only multiplication fact other than other than 1 times 4 that would give you your composite number of 4. So again, let me try this, and you guys are probably going to laugh at me. Let's see. Oh yeah, look at that. So you've got a 2 and a 2. I'm going to erase these ugly old weird circles and try this. So again, as you can see, when you have your prime factorization all worked out, you actually get the exact same thing. It doesn't matter what facts you use when you're breaking down your original number. You should still get the exact same prime factorization. I still get 2 times 2 times 2 times 2. I still get 4 2's at the end. Okay, one more. So this one, it doesn't have that pre-made layout, so remember you can use whatever you want. If you want to pause the video here and then let it play to see how it works out in the end, that's fine. So I would actually pause the video here and break down that number and see if you got the same thing as I did. Okay, we're back. So you should have gotten a factor tree that looked similar to this. You may have used 3 times 21 to start yours off, and again, you should have gotten the exact same answer. So when I write my expanded form, that's going to be 3 times 3 times 7. And then with my exponential form, I should get 3 to the 2nd power, because again, that first big number, the big number is your base. It's telling you what's repeated, and then the exponent tells you how many times. So I should have 3 to the 2nd power times 7, okay? Okay, so here is the one that I think you guys are probably most interested in. So, Ms. Simmons, what do I do when the number that I start with is prime? Because you may notice that 19 doesn't have any factors other than 1 in 19. So, here's the thing. Remember, 1 is not a prime factor. It's just not. Okay, but in the case of a prime number, what you have to do is list 1 and 19 as their only factors. And you don't want to circle the 1, okay? You don't want to circle the 1 because it's not prime. But 19 is a prime number. And when you write it in expanded form, you would just write 1 times 19 equals already prime. Okay, so this is already a prime number, which means that when you write it in exponential form, it would literally just be the number 19. Because really the only factors it has, again, like I said, are 1 in itself, but 1's not a prime number. And remember, prime factorization tells you that you should have prime factors. 1 is not a prime number. Okay, so be careful with this type of problem. All right, moving forward here. Okay, so now if you need to take a break, then pause for a second, and then come back because we're going to go into GCF next, okay? You may have done GCF last year, so again, if you need to take a break, pause now. If not, then we're going to keep going, okay? So greatest common factor, if you break this phrase, it's 3 words, so I can't say this word. If you break this phrase down and actually just look at what it means, you could make up your own definition because we know what a factor is, and then you should have prior knowledge of what greatest and common mean. So if you were going to break it down literally word for word, another way to say greatest would just be biggest. So it's the biggest. And then factors are numbers. So the biggest number that two, what we would have to say is products, because remember, whenever you multiply factors, you get a product. So the biggest number that two products both share. So I know that that's a little bit confusing right now, but keep going. So another definition that you could use is the biggest number that divides evenly into both or all of your original numbers, because sometimes you're given more than 2. Sometimes you have 3 numbers that you have to find the greatest common factor for. Okay, so keep in mind that we are using prime factorization for GCF. In the past, you may have used something called the rainbow. Miss Simmons doesn't particularly like the rainbow method because to me it's messy and it leaves a lot of room for error, okay? So if you don't know what the rainbow method is, that's okay. We're going to use greatest common factor with prime factorization, which again you may not be familiar with, but that is okay. So I'm going to make myself a little work area over here so that you guys can see where I'm writing and what I'm writing. That's pretty bright, isn't it? Oh well, at least you can see it. Alright, so when I'm finding greatest common factor, I want to start with the factor trees. Okay, and remember, I've got a Venn diagram here, and with a Venn diagram, in the middle you place things that both of your 2 listed items have in common, whereas on the opposite side, so like on the left side where my 12 is placed, I would place everything that 12 has that 30 doesn't. And then on this side with my 30, on the right hand side, I would place everything that 30 has that 12 doesn't. So again, I'm going to break down these numbers, and I guess I'm going to switch from red because it's kind of a harsh color. Alright, so I'm going to start with my base number, which is 12. And again, I want to break that down into its prime factorization. So let me do that. So let's break it down. So I want to use, let's say 6 times 2. That's the multiplication fact I want to start with because I know that that equals 12. And I also know that 2 is prime. So I'm going to go ahead and put my circle around 2. But 6 is not prime, so I need to continue to break that 6 down. And that's going to give me 3 times 2. A 3 and a 2. Okay. So with 3 times 2 here, those are both prime as well, so I got to circle them. Woohoo! Alright. So when I write that in expanded form, and you're going to want to write this in expanded form, okay, that's 2 times 2 times 3. Now I need to break down my 30. Okay, so 30. And then I know that I could do 3 times 10. That's the first thing I'm going to do, I think. So 3 times 10. That one sounds good. Okay. Now I know that 3 is prime, so I'm going to circle that. But 10 is not. It can be broken down further. Okay. So 10 can be broken down into 2 times 5. And both of those are prime. Woohoo! We're really rolling, y'all. Okay, gotta write that in expanded form as well. That would be 2 times 3 times 5. Okay, so remember how I said with the Venn diagram you want to list all the things that they have in common. Okay, in common. So looking at their expanded forms, looking at both numbers' expanded forms, what I can see is they both share a 2. Okay, they both have a 2. So I'm going to list 1, 2 in the middle, because when you're looking at this, you only want to list how many things they have in common. They have 1, 2 in common. 30 does not have this second 2 that 12 has. So I'm going to cross out those 2's because now they've been used. Okay, so going on down the list here, I see another 2, but again, there is not another 2 listed in 30's expanded form, so I need to move on. Now I've got a 3. I can see that 30 does have a 3, so I want to list that 1, 3 that they both share in the center. Okay, we're really moving, y'all. So I'm going to cross out that 3 because I've used it. Now the only things left are the 2 and the 5. Okay, and they do not share another 2 or a 5. So I want to list those on the correct sides for whom they belong. So the 2 was out of the 12 and the 5 was out of the 30. And the only place I want to look, because I'm looking for common factor here, are the things that they have in common, so that would be in the middle. Now in the middle here I have both a 2 and a 3. And what I want to do with those is multiply them together. So what is 2 times 3? Well, 2 times 3 I know is 6. So the greatest common factor of 12 and 30 is 6. Okay. The reason I like this prime factorization method is because you can actually do least common multiple with this as well. So we're only focusing on greatest common factor for today, but tomorrow when I come back, I'm going to teach you guys least common multiple. Okay, so get really good at this greatest common factor thing. So we're going to keep going. You've got 16 and 32. So again, I want to break down those numbers into their prime factorization. So if you want to see if you can do this on your own and then just kind of either fast forward or pause the video and wait and watch me work it out later, then go ahead and do that. You can pause it here and then see if you get it right. But I'm going to keep going. So if you don't want to see it right now, then pause. All right, so I'm going to break down 16 and I'm going to break down 32. Okay, so 16, oops, I don't want that. I want just a regular line. 16 can be broken down into 2 times 8, which is the first thing I thought of for 16. But again, if you thought of 4 times 4, go with it. Okay, so I know that 2 is prime, so I'm going to go ahead and circle that. Awesome. Okay, 8 can be broken down into 4 times 2. So I'm going to do that. Got a 4, and I've got a 2. And again, 2 is prime. So I'm going to go ahead and circle that. And then 4 can be broken down into 2 times 2. 2 times 2. Boop. Okay. And I'm going to circle those 2 2's as well. And I didn't leave myself much room to write this expanded form, did I? Oh well, I can write it underneath it. Okay. So my expanded form for this would be 2 times 2. Don't want that time symbol. There we go. 2 times 2 times 2 times 2. And we kind of already did that one earlier. So for 32, I know I can break that down into, let's see, 2 times 16 or 4 times 8. I think I'm going to pick 4 times 8. Okay, and neither of those are prime, so I've got to break both down. Okay, that's going to be 2 times 2 for the 4. And both of those are prime. Yay, circle. And then 8, got to break it down a little bit more. So my lines are getting a little wonky. So I've got a 2 times 4. And again, it doesn't matter what order you do this in, guys. You should all get the same prime factorization at the end. So I know 2 is prime, but 4 is not. Gotta break that down. Whew, this is a funky looking tree. Alright, 2 and a 2. Awesome. And those both need to be circled because they are prime. Woohoo! Okay. So the expanded form of that is going to be 2 times 2 times 2 times 2 times 2. You can't see my 2 because it went behind the trash can. There it goes. Okay. So 1, 2, 3, 4, 5. Got to make sure. 1, 2, 3, 4, 5. Cool. All right. So looking at their expanded forms, you can see that they're very similar. They both have a lot of 2's. And just how many 2's do they have in common? Well, let's take this 1, 2 at a time here. So I've got the first 2. Goodbye. Goodbye. Got the second 2. Awesome. Goodbye. Goodbye. Got the third 2. Got a lot of 2's here. Make sure you know that you're not writing 22 on your paper. And then they have one more 2 in common. So they had 4 2's that they shared. That's a lot of 2's. So bye 2. And you've got this one extra 2 just kind of hanging out with the 32. Okay, so in the middle, again, you want to find your greatest common factor by using what's in the center. All right, so the greatest common factor is going to take me having to multiply all of these together. So the GCF would be 2 times 2, which is 4, 4 times 2, which is 8, and then 8 times 2, which is 16. Oh boy. You notice that one of your factors, or your original products, was 16. Helpful hint, if you notice that when you're doing greatest common factor, if the smaller number you're dealing with is a factor of the larger number, you've already found your greatest common factor. All right, one more. Okay, so you've got 15 and you've got 22. So I'm going to break those down. And I'm not going to draw my nice boxes out to the side. I'm just kind of going to go for it here. So with 15, I've got 3 and 5. And thank you. Those are already prime factors. Yay me. Okay, less work. 3 and 5. Yay, got to circle them. Woohoo, 3 and 5. So my expanded form is going to be pretty short here. My expanded is going to be 3 times 5. Woohoo! Okay, and 22 is my other number here, 22. And when I break that down, the only thing that 22 can be broken down into is 2 and 11. Both are prime numbers, so again, I had that one pretty easy. Okay, so the expanded form for this, again, is going to be pretty short. I've got 2 times 11. Okay, so let's compare these expanded forms. You can actually move them so that they're right beside each other, and it might be a little bit more helpful. Okay, so when you're looking here, they literally have no factors in common, like none, nothing. Okay, so when that happens, all of your factors that you have just kind of go into the opposite sides of these, this Venn diagram. And then in the middle, the only greatest common factor it could have is 1. Okay, so the greatest common factor for this problem is 1. If they share nothing in common, their greatest common factor is automatically 1, because 1 is a factor of every single counting number. Now remember, 0 is not a counting number. It's not a counting number, so you cannot use that as one of your factors. 1 and up only. Okay, so your keywords for GCF. This is talking about word problems. And I know we're going really fast here, guys, so just kind of bear with me. They're very easy. They're actually super duper easy. You're going to look for words like, I don't want brown, that's gross. All right, you're going to look for words like greatest. So again, that's in the word itself, greatest common factor. Biggest, largest, most, maximum. Okay, these words are all, excuse me, these words are all synonyms. They all mean biggest or greatest. Okay, you may also see the scenario where somebody is wanting to make equal groups. Okay, that should tell you that you're finding the greatest common factor here. If something is being distributed evenly, I can't spell. Distributed evenly. You guys know I'm not the greatest speller. That also indicates greatest common factor. Please write these down. Okay. Okay, so the last thing we're going to do today, and I know this is a really long video, thank you guys for hanging in there, is word problems. So looking at this nice problem here, You've got Lindsay has a bag of 36 orange flavored sweets, and Evie has a bag of 44 grape flavored sweets. They have to divide up the sweets into small trays with equal number of sweets. Each tray has to contain both orange flavored and grape flavored sweets only, meaning there's not any mystery sweets that are coming in. We're just using what we're given. So we don't want a remainder, but we do want the largest possible number of sweets in each tray. So essentially what we need to do is figure out how many trays she can actually make. So our question here should be, how many trays can Lindsay and Evie make, or Evie, excuse me, and Evie make without having any sweets left over? Okay, so what I'm going to want to do is find the greatest common factor. So find that greatest common factor of 36 and 44. Okay, so in here you really want to highlight or underline those keywords or the important information. And what I see in here is that divide up, and I also saw the word largest, so that keys me into finding greatest common factor. So pause now and find the greatest common factor of 36 and 44. So go ahead and pause your tape and then come back to us. Okay, so you guys should see my work below. So I broke down 36, and remember, it does not matter what multiplication fact you chose to begin with. You should still have the same expanded form as me. And then I broke down 44, and then in my Venn diagram I placed the two things that were in common, which in this case were the two 2's, and then you multiply those two 2's, because remember they have 1 2 and 1 2 2's. Please do not place all 4 2's in here. That is going to give you the wrong answer. Okay, so I found that the greatest common factor was 4, so they can create 4 trays without having any sweets left over. Okay, so on the next page it's going to be another similar question, but it's a little bit more in depth. Okay, Kate has decided to make party baskets for the fundraiser. Balloons are sold in bags of 20, party horns are sold in bags of 10, and there are 8 candy bars in a package. So how many bags can Kate make if there are an equal number of balloons, horns, and candy bars in each basket? Okay, so what that means to me is I do need to find those keywords. And again, I see equal number. That's the first thing that jumps out at me. So I need to find the GCF, which is going to be the number of baskets that I can make. So I have 3 numbers here, so I've got to break all of them down. I've got 20, I've got 10, and I've got 8. Now thankfully these are pretty standard numbers and they shouldn't take me a very long time to break them down. But go ahead and pause the tape for a second. And I keep saying tape. Pause your video. Sorry, I'm old. Pause your video and break down these numbers. Okay, we should be back now. And as you can see, I broke down all 3 numbers, wrote their expanded forms down here, and it is really helpful for you to stack them up like this. You guys know how I like to stack my numbers most of the time. And what you will want to do is make sure that since you've got 3 numbers, that you're looking for what all 3 of them have in common. All 3 of these numbers have to have the same factors in common. So I see that they all have at least 1 2 here. Okay, so looking down the line at the other expanded form, what I can tell is that, okay, well, 20 has a 2 and 8 has a 2, but there is not a third 2 here for 10. So they do not all 3 have that in common. And again, we've got a 5 in the 20 and a 5 and a 10 in the 10, but there is no 5 here in the 8. So the only thing they have in common is a 2, which means that their greatest common factor is 2. Okay, and that's going to be 2 baskets. Because remember, we want to include units here, guys. So we're going to take this a step further, and we know that we have 2 baskets, but now the question becomes how many balloons, horns, and candy bars will be placed in these baskets. So if you know that you have 20 balloons, but you need 2 baskets, what you want to do is take that greatest common factor and actually divide. So 20 divided by 2 would tell me that there are 10 balloons in each basket. Okay, because 10 times 2 would give me my original 20. Then take that 2 again. I've got 10 horns. 10 divided by 2 would be 5 horns in each basket. And then the last one is my candy bars, and you started with 8, and then I've got to split those between 2 baskets, so that means there are 4 candy bars in each basket. All right, guys, that's the end of the lesson. I know it's kind of long, and thank you for hanging in there with me. I hope that you guys are feeling okay about this. If not, I will be back tomorrow. We will practice. I will answer any questions you have. I hope you have a great day, and I will see you guys tomorrow.